Hey Chem students, if you're watching or listening to this or both, you're ready for Learning Goal 3.18, which deals with energy in reactions. And you should have already read and answered some questions about endothermic and exothermic reactions. And what I'm going to do really quick is run through how we can take actual chemical equation reactions that you've been representing, along with what you know about exothermic and endothermic, and model them on our energy bar diagrams, which we used in Chemistry A, when a physical change was occurring, when things heated up, cooled down, or when they changed state, solid to liquid, liquid to solid, or liquid to gas, or whatever it might be. So these diagrams should look kind of familiar, except we're going to focus this time on ECH, because ECH represents chemical energy. And if a change has occurred, there has to have been a change in the chemical energy. That's the only way that bonds can break or new bonds reform and things rearrange, is for a change in that chemical energy. So we're going to start with this first example, decomposition of sodium hydrogen carbonate. And here's what this reaction looks like right here. Now, without this first part, this is what you've been practicing writing, and it looks like what a decomposition should look like. The substance breaks down into these parts. Now, in order for this to occur, you have to heat it. You have to put it in a test tube, put it over a Bunsen burner. And so we've added the word energy here. We have to add energy to these reactants to get this to happen. And so what that means, just like it says here, is that the products, they store more ECH. They have more chemical energy stored in their bonds than the reactants. So we had to supply energy for this to occur. So the focus that we're going to have on these bar diagrams, like I said, is ECH. We're going to be dealing here and thermal. No EI. EI is relevant if there is just a physical change of state occurring. And right now we're dealing with chemical changes. So here's what we start at. Here is my heating in, because I had to heat this up, so there's energy flowing into the system, and that gets added to the chemical energy, because again, we know in this reaction, the products contain more energy than the reactants. Now here's a picture that you saw in the reading. This is another way that this reaction can be represented. E stands for energy, and so the reactants are lower than the products at the end. Now we're going to take these diagrams one step further. So here at the bottom I have an example of that. This looks the same as this one here, and the very last bar diagram looks the same as it does here. But what we're going to add in is what's happening during the reaction, because E thermal has to change at some point in time, because up here we added some thermal energy. So we start off low. We add energy into the system through the heat, through the flame, and that's going to cause the thermal to go up, obviously. If you heat something up with a flame, it's going to cause the thermal to skyrocket up. So I have a large bar here in the middle. And so notice this says reactants hot now. Well, it's this heat energy then that causes the change to occur, and so then we have an arrow pointing to the ECH in order to get to our final large bar ECH that the products have. So notice the amount of thermal that went from here to here is the same as it shows up on this side. The other thing that you could jot down about this reaction is that this is an endothermic reaction. When energy goes into the system and the products are higher energy than the reactants, it's endothermic, and that should match what you read about. Let's go through another example. This example is combustion of methane. Anytime you have a combustion reaction, it is exothermic, as it states right here. This reaction is going to give off energy. Combustion reactions give off a tremendous amount of energy. That's why we use methane as an energy source. So here's the equation for the combustion of methane. This time, notice, the plus energy shows up on the product side, because again, that's one of the things that's given off in this reaction. So, because of that, we know the reactants start out with a very high ECH. That gets transferred to thermal when the change occurs. So in the middle then, the products are going to be very hot, lots of thermal energy, and then that thermal energy is going to get released till eventually everything's back to equilibrium, back to the normal temperature. Temperatures want to flow from hot to cold, so it's going to flow out of the system. This is extra energy these products don't need anymore. They've changed, they hold a lower amount of energy than the reactants did that they started with, and so that extra energy gets released as heat. That's why we can roast marshmallows at a campfire, that heat that gets released from the combustion. Again, this is an exothermic reaction, so here's a way to show exothermic reactions. High energy on the reactants, lower on the products, and again, that's what causes the release to occur out of the system. Okay, one last example, and you can read through this, but this has to do with energy cold packs, or chemical cold packs. The ones that you break, you're actually causing a reaction to occur, usually with ammonium chloride in it, and it then feels cool. So like it says in this little reading, if you get a sprained ankle or something, you can put that on there and it feels cool. Well, the reason why it feels cool is because that system is taking energy into it. And so this is an endothermic reaction. It's an endothermic reaction. So it seems weird to think that if a system, if it feels cooler, how is it that it's absorbing energy? But that's what we feel as being outside of that system of the chemical change. So here's the start. Since it's an endothermic, our CH starts lower than the end. There's a transfer from thermal to chemical. And then notice this energy flow into the system to bring that thermal back to the level it should be, like normal level. And again, because you're on the outside of the system, you feel cool, hence the term cold pack. So again, this is an endothermic reaction. The products inside that cold pack are holding more energy than they did before the reaction, and they're getting that energy from outside the system, and to us that feels cool then. Notice that in this one, the energy flow occurred here, the second part. So we don't even need this first energy flow. That's different for some of these. For example, let me go back up. Same thing here. The energy flow happened after the reaction changes were occurring. But I think on the first one, we had to have energy flow right away in order to get this decomposition to even happen. So those are things to consider also. So there's another link on this section of a worksheet that gives you descriptions like this, maybe some practice writing those equations, I believe, and then drawing these out in terms of matching up what's happening and what you know about endothermic and exothermic. And then I have the key up front. The quiz for this section then is you're going to actually perform some endothermic and exothermic reactions, write out all the equations, diagram them correctly, and make some graphs. So be ready for that. Let me know if you have any questions about these notes. I'm going to also post this Word file in case you want to print that and have a copy of it. It's a good place to jot down notes and ask me if you have any questions.